Let's start. So I'm going to consider today atomic system, which is essentially a hydrogen atom in external fields. So until now we just looked at structure of energy levels of an atom, and this structure was, we considered that from a different actors that are in the story. So we considered, of course, the gross structure that was related to a Coulomb field. Then we added some more subtle interactions that were derived from relativistic physics, and that gives us the fine structure splitting of levels. And then we added effects that are connected to nuclear physics, or to something that was related to a nucleus, to proton and neutrons. So there are several effects that are connected to the nucleus, so we consider it spin, essentially. But of course we also considered the finite mass of the nucleus. Additional effect you will see in homework that's related to the size, the finite size of the nucleus. This gave us essentially the structure, the level structure of the atom. We saw that there were some, this subtle effects give some finite splittings of levels, shifts of the levels. So now we can see that there are more interesting structure than only considering Coulomb field. Now what we want to do is just to take this atom as it is, so as we know it now, and put it inside the magnetic field. And later we will do that for the electric field as well. So there is external field. So somebody made this field. So now we want to see what's going on with the energy levels of the atom once the field is on. Okay, so the magnetic field is on. There are several regimes that we have to consider. So these regimes, of course, are related to the Hamiltonian that we are having in the system. So if you remember, the Hamiltonian that we have has several parts now. So this Hamiltonian includes Coulomb interactions that we noted as H0. So there is a kinetic energy and a Coulomb interaction inside this H0. Now plus the correction of the order of fine structure constant squared due to the relativistic effect. This correction was called as a finite structure corrections, plus additional corrections that was even weaker than fine structure. We call it hyperfine structure. Hyperfine effects, they are related to nuclear effects. So this is essentially the Hamiltonian that we want to consider. But now, in addition to this parts of the Hamiltonian that we already had, we have to add an additional part, which is related to the magnetic field, which is the external magnetic field. So the interaction of this magnetic field with the system is, of course, goes through the interaction with some angular momenta. So the angular momentum of the electron, spin of the electron, and spin of the nucleus. So now it's, of course, proportional to the magnetic field multiplied by the magnetic moment. But now, depending on the strength of the magnetic field, this part of the Hamiltonian can be different as compared to different parts of this Hamiltonian. So for example, if we consider a very weak magnetic field, that would be a regime of weak weak interactions, then we can consider all these Hamiltonian as a part, as a single Hamiltonian that we know already the eigenstates and eigenfunction of this Hamiltonian. And then we can consider this part of the Hamiltonian as a weak perturbation. And then we can solve that using the perturbation theory. So this will be considered as a weak field regime. Now, weak field regime means that we are having magnetic field which is relatively weak. But historically, this regime was called Anomalous Zeeman. Anomalous Zeeman. Anomalous Zeeman effect. Essentially, all this story of considering atom in the magnetic field has this name in it of the German physicist Zeeman that found first that if you take an atom and put it in the magnetic field, you see that the energy levels split it in many different sublevels. That was at the end of the 19th century. It was 1896. So nobody knew that time what exactly the structure of the energy levels of atom. And by some funny reason, so this regime, which is essentially a perturbative regime, was called essentially anomalous because nobody understood why it looks like as it looked. So it looks like a very complex structure. If you go to a stronger field, you see less splitting, and you understand this splitting more easier than what is going on at the weak magnetic field. So we will see that today. So then next regime is essentially the regime when this Hamiltonian would be of the order of hyperfine splitting, right? So when this part is of the order of this part, then it's of course we cannot consider this Hamiltonian as a whole and then consider this as a certain perturbation. We have to consider this Hamiltonian as a whole, but then we have to consider these two parts as some mixture, and most unfortunately this one and that one has a different basis wave functions. So we will have to understand how to deal with that. And then we'll go to the next regime where this Hamiltonian actually is larger. So this one we can call as an intermediate field limit. Mediate field limit. So this limit corresponds to the story when the magnetic energy, this HB, will be of the order of hyperfine splitting. But it will be still much smaller than this one. So we can consider this Hamiltonian as a whole. So then we are going into an additional limit that we consider as a strong field limit. Strong field limit. So strong field limit means that we are, the magnetic field is actually, this part of the Hamiltonian is even larger than the hyperfine splitting. Sorry, the fine structure splitting. But it's still smaller. Well, the better way to do that is to write it from the other side, right? It's larger than fine structure, but it's still smaller than the energy levels of high n number. So what we call the Rydberg atom. A Rydberg atom is just a name of any atom. It can be also a hydrogen atom, where the electron is put on a very highly excited orbital, where the n principal quantum number goes to a large number, so of the order of hundreds or more. Okay, so this is considered to be a Rydberg atom. Okay, so now this is the strong field limit. Okay, in this situation, actually this Hamiltonian is larger than these two parts. So we have to consider this Hamiltonian first as compared to the Coulomb energy, and then we have to consider these two both. Okay, so these two, and then the last regime that can be considered here, we will talk about that. And this is the regime of extreme limit. So this is the extreme. So the extreme limit is when the B Hamiltonian, or this energy related to the magnetic field, is of the order of a Rydberg atom. So it's a really strong magnetic field. So this strong magnetic field actually starts to destroy the Hamiltonian H0, right? So it starts to distort the Hamiltonian H0, starts to distort the Coulomb interaction. So it essentially starts to destroy the central symmetry of the problem, and the angular momentum L becomes not a good quantum number. So you can consider that as essentially going from here to here, you start to destroy one after the another good quantum numbers, and you have to replace them by something else, right? So here, for example, if you remember, last week we introduced the quantum number F, which is the sum of all angular momentum of the problem, L, S, and I. So here in this regime of anomalous Zeeman effect, we have still the regime where the quantum number F is a good quantum number. It remains a good quantum number. So this is corresponding to HB, much smaller than the H hyperfine. In this regime, F is still a good quantum number. Here, F is not a good quantum number anymore. So we have to consider J, which is the sum of L, the odd S, as a good quantum number. But I has to be removed from this story and considered independently. So this is what we need to do in this regime. So this regime actually splits J. So J is not a good quantum number anymore. The good quantum number still is L. L will be a good quantum number, but S and I should be considered independently. Okay. So in this regime of the extreme limit, L is not a good quantum number anymore. So we start to distort the Coulomb potential. So we will consider each one of them today, and you will see how we can treat this interaction. Part of this story is also in the homework. Okay, so let's start from the weak field regime. Seems like a simple regime, right? But actually, it's the longest one to deal with. Okay, so now let's try to do with the weak regime. So we start with the weak field. So we know how to write the Hamiltonian of the interaction of the magnetic field. So essentially, this Hamiltonian is minus all magnetic moment which is involved in the story. So the magnetic moment that we have is the magnetic moment of I, of the spin of proton, if we are talking about a hydrogen atom, only proton, plus ms, which is the magnetic moment of the electron, plus ml, this is the orbital angular momentum of the electron, multiplied by b, the magnetic field. So that's the Hamiltonian, right? So that we have to solve. Is that all? No. That's not totally correct. It's correct for most of these regimes, but it's not correct for the extreme limit. So there is something is missing here. What is missing here? So the missing part here is that we actually build the Hamiltonian by our classical intuition. This is wrong. So classical intuition is not always correct. Okay? So the classical intuition says that this is what we have to do, but this is not correct from the quantum mechanical point of view. Quantum mechanical point of view is the point of view of energy. So you have to go into the canonical momentum in order to treat magnetic field correctly. So the Hamiltonian that you has to be to write in this story is the Hamiltonian that the kinetic energy is affected by the vector potential, right? Yes. So the vector potential is the correction part that has to enter into the quantum mechanical kinetic energy, and that would be the correct way to describe the interaction between the system and the magnetic field. Okay, so if we consider that, so we are going to write, instead of p squared divided by 2m, that's the kinetic energy part of the Hamiltonian here, right, h0. So this kinetic energy should be replaced by the canonical momentum, and this canonical momentum is the p plus the electron charge multiplied by the vector potential, and thus this should be squared, and this will be the correct way to deal with magnetic field in quantum mechanics. Okay, so now from here we can actually derive this Hamiltonian and see that this Hamiltonian is not correct. Okay? It does not include everything. So to deal with that, we need to write down this quadratic part. So this quadratic part gives us p squared divided by 2m. That's exactly the same part that we started with, so without the magnetic field, plus E divided by 2m. Now it's multiplied by P A plus AP. So they not commute, right? And plus an additional term, which is the square of this part, right? So this is the E squared divided by 2m multiplied by A squared. Now, what we can do, so we can do here, we have to consider this part, right? In order to see how to treat that. So this part is essentially, so if we consider the P, right, it's the operator, which is the H bar divided by I gradient. Is there a minus here or not? I will yeah, I think that there is no minus, but we'll check that in continuous. So now it's this guy should be replaced with here. So what we have here is this operator gradient and the multiplied by the vector potential. So this part has this so we can write it like that. So if we get this in the story, so this should be minus h bar squared divided by 2m minus the Laplacian. Now it's minus I h bar e divided by 2m. And now it's multiplied by the gradient, or that is divergence of A, plus A multiplied by gradient. So this is something that we have to deal with. So, and then in order to do that, we actually have to understand, right, that this guy is applied. So this is the operator. So I'm leaving this part alone because there is no P there. So this should be added here. But now, if you consider these operators, so you have to remember that this operators is applied on the wave function. So if I'm doing that, right, so if I'm taking divergence of the vector potential which acts on the wave function, so this is something that I can describe as a divergence that works on the wave function multiply plus the gradient, the A, multiplied by the gradient that works on the psi. Now, this guy we can consider as a gauge. So now we can choose, or have to choose the gauge, certain gauge. So we choose the gauge where the divergence of the vector potential is equal to 0. So then this part drops down. But we have another one, which is the A multiplied by the gradient. And this is the same that we have here. So then this one plus that one gives us a factor of 2. So the factor of 2 cancels here. So we will have twice this term twice. So 2 times larger. So if I continue this story, then I will have the minus h bar squared divided by 2m multiplied by Laplacian minus I h bar e divided by m multiplied by a multiplied by a gradient. So this is what is left, plus this term that I'm not writing. Now we can see what is this, right? So this one, in order to understand what is this, so we have to remember what the magnetic field is. If we have a uniform magnetic field, right? So then the A multiplied by gradient is essentially the 1/2 of the vector potential of the uniform magnetic field is just the B cross R 1/2, and then this multiplies by the gradient. So now we have to get back from the gradient to P through this operator, right? So we can get it back. And what we will have here in this story is that if we exchange, right, this B with the operator gradient, we will have the 1/2 of B multiplied by R cross gradient. And if we replace the gradient here by P, we have here R cross P. P has the velocity inside, R cross velocity gives you the angular momentum, right? So if we are doing that correctly, this guy should be equal to, so this gives us L, which is equal to minus IH bar R cross gradient. And then we can get here the term at the end, which is the minus 1 over 2I H bar B multiplied by L. So here you see this term of the Hamiltonian that is written here by the classical intuition. It's actually derived from the canonical quantum mechanical treatment of the interaction of the system with the magnetic field. Okay, so, but what you see here is essentially only this part, which is related to angular momentum, right? So this is only angular momentum. There is no spin of the electron, spin of the nucleus. So these guys should be added. Right for now, phenomenologically, but it's of course can be treated also strictly. But what we are interested actually in, so not in this part especially, because this part you actually, you already know from your classical intuition that it should give this guy. But what we are interested in is the additional term that we dropped from the consideration. It's here. So this Hamiltonian is wrong because it misses the additional E squared divided by 2m multiplied by A squared. So for this term, actually, I did all this consideration because this usually you could believe me without the treatment of the classical mechanics. So you know that this is correct. But this guy comes actually from the real treatment of the problem due to the quantum mechanics. Okay, so now I can remove that. This was sort of by the way reminder. And we don't need also this guy. But what we need is this Hamiltonian that now is correct. It includes everything. And it excludes this quadratic term in the vector potential. This quadratic term is very small, usually. So it does not walk that much until you actually hit the extreme limit. So we will see it start to walk for very strong magnetic field. For weak magnetic fields, this story can be neglected. Okay, so it's usually a very small corrections. Okay, so now what we need to do is essentially to go to the weak field. So now this is the Hamiltonian. So we work hard to add that. So it's not important here in the weak field. So we can drop it back. And we can consider only this part of the Hamiltonian. And then we can actually also drop another one. So this part is, you know, that the magnetic moment of the nucleus is very small. So it's only, it's 2,000 times less than the magnetic moment of of the electron spin. So therefore, we can neglect that. So this part. So what is left in this story is only this guy. So the Hamiltonian that we are going to work with is only includes spin of the electron plus the orbital angular momentum of the electron. Well, we drop that, but the F number is still correct. So we drop the sort of interaction of the magnetic field with the spin of the nucleus, but it's still, the nucleus spin is still here in this Hamiltonian. So it goes nowhere. So it will be still there. Okay, so now this is the Hamiltonian that we want to consider, and we want to understand how to actually find the, the expectation values or eigen energies of this Hamiltonian together with this, right? So what we are considering is the weak limit. This means that this story gives us the energy levels that we know, and we know that the quantum number, the good quantum number here is F, which is the sum of L plus S plus I. And this part is essentially a perturbation that we want to find this perturbation. So we want to find, actually, according to perturbation theory, the expectation values of this Hamiltonian within the wave functions of a hydrogen atom. So something similar to what we did until now with different types of interactions. Okay, so now what we can say? We can say that this is essentially, if we continue, can be written as a certain angular momentum, A, MA, which is the sum of both of them, multiplied by B, and we know that MA, we can write it as the sum of minus mu B divided by H bar, so that's the Bohr magneton, multiply by L, that comes from the angular momentum of the electron, plus GS multiplied by S, and from today morning at least, you know that GS is not equal to 2. It's a bit different from them. But we will drop this correction. It's small, so we will consider it as a 2. And so now what we have in this story, so we see that the interaction of the magnetic field with the spin of the electron and the angular momentum spin has this L vector and S vector in the story. But this Hamiltonian, all three of them, the good quantum number is the sum of them, the F. So somehow I have to go from all this L and S into the F, the quantum number F. So that's the idea. So we can we start from the beginning. This is the J vector. J vector is just the sum of L plus S, right? So and this means that L plus GSS. So L plus GS, gyromagnetic ratio of the electron, multiplied by S is equal to J minus essentially, plus the J is just L VOD S, and it's one time S, and here I have 2 times S, so I have to do the GS minus 1 multiplied by S, right, in order to keep this part the same. So again, we know, or you know, we all know that GS is not equal to 2. It's a bit corrected as compared to that. But I will take it GS as very close to 2. So it will be 2 for me for today. And then I can just say that this is j, this is vector j plus s, right? This is what I want to say. So L plus gs multiplied by s is just equal to j plus s. That's the story. Okay, now what we can do. So we have to make the expectation value of this operator, right? So the operator, the magnetic moment operator is now the sum of j by s. So I have to calculate the expectation value of j and s. So how to do that? Essentially, in order to do that, we need to recall a theorem that the matrix element, or expectation value of the s vector, or the mean value of the s vector, can be actually projected to a different vector, to j, s multiplied by j, and this will be multiplied by j again, the mean value, and there is a multiplication factor, which is the h bar squared multiplied by j plus 1. Essentially, this is something that reminds you very well the Wigner-Eckert theorem that we used a week ago. So it's essentially one of the different types of Wigner-Eckert theorem, how to write it. It means that we can take the vector s, and so the meaning of that is just, we can take the projection of this vector s on a certain value. So it means that's essentially what this means. So if you take s plus l, and we have this j vector, that's what we do here, right? So we define the j vector as l plus s. So we say that the mean value of the s vector is directed along the j vector. That's what this theorem says. So the meaning is clear. So this means that, if you consider the quantum mechanical system, so there is a precession of any angular momentum. So this angular momentum also precesses around the some quantum axis. So this precession means that the mean value of this vector will be indeed directed into the direction of the j, if you consider this time averaging of the story. So this is the meaning of this theorem. So I'm not proving that. So if you wish, you can go and to angular momentum theory and find and prove this theorem, especially if you want to calculate this factor. But this factor is very, very close to the same factor that we saw in Wigner-Eckert theorem a week ago. Okay, so this is what we are going to use, this theorem. So now we know that this is the multiplication of s multiplied by j and j. So you know why we like this theorem, right? So because there is a multiplication of s and j. So this is something that you can easily produce, because multiplication of s plus s multiplied by j comes from here, right? So j plus s squared will give you what you are looking for. Okay, so that's what essentially we have. So this j plus s, or L plus gs multiplied by s, this mean value of this vector is just equal to mean value of j. That's from here. And we have this s we replace by this part. Okay, so and this part will give us plus this multiplication gives us 1, and then we have this sj j divided by h bar squared j plus 1. Okay, now what we do is a known trick, right? So we take the L squared and say that L squared is equal to J squared plus S squared minus 2J multiplied by S, right? And now we can say that this is exactly the multiplication of Js, so we know that this is the sum of operators L squared, J squared, S squared, and this is multiplied by J. Therefore, this guy essentially will be equal if I continue. So J I can take out of the story. There will be 1, and there is a minus, right? Minus this story, which gives me the L. So L squared give me L multiplied by L plus 1 minus J multiplied by J plus 1. Well, I'll leave it large values. Minus S multiplied by S minus plus 1. This is divided by 2J, J plus 1. And all this is multiplied by mean value of the vector J. So this is essentially what we get once we consider the operator of the magnetic moment. So we have a certain factor that we can calculate. Okay, so we know what is L, what J, what S. So this is a gyromagnetic ratio, corrected gyromagnetic ratio, when we consider this story. But this is not the end of the story, because remember, we only considered 2 spins yet. So we considered only the angular momentum, and we considered the spin of the electron. So this is not the end story, so we have to continue it a little bit. But before I'm doing that, so I just want to say that this should be equal. So we call this guy as a GJ, gyromagnetic ratio of J, GJ, and then if we know that, so now the Hamiltonian HB, the expectation value of the Hamiltonian of HB, is actually equal to GJ and multiplied by GJ multiplied by expectation value of J multiplied by B. Right? And so, and this is a bad guy, right, in the story. Why this guy is bad? Because if you remember, this part of the Hamiltonian did not like J. We don't have J vector in the story. So we have F. F is not only L VOD S, L VOD S VOD I. So this is why it's not enough. So we have to go further. And treat also to add into this J, the F. We have to go to F, because F is the correct quantum number for this part of the Hamiltonian. Okay? Okay. So if you agree with me, let's go there. So it's more or less a repetition of what we did now, but with a little difference. Ooh, disappeared. Right, it disappeared somewhere down, right? No. Or it's gone. Indeed. This is a good magic. A perfect one. I choose the correct position to stay. Okay. Okay, so let's go further. So in order to go from here, right, to f, we actually use the same trick, because we want to calculate here, right, the mean value of j. But we don't want j, we want something else. So we go and use again this same theorem. And we introduce the factor f, right? This is what we want. So essentially we say that gj multiplied by j, this is the expectation value that we want to, or mean value that we want to measure, or we want to know. This will be equal to gj multiplied by f multiplied by j, mean value of f, right? Divided by h by square f plus 1. Okay, so we use again this theorem, right? So using the same trick, so we can say that now we want to say that f is actually equal to j plus I, right? And we can extract here, right, from this story is the multiplication of f multiplied by j. So if you of course change the so it's what we do, yeah, right. Value of f. Well, the combination will be, well, this of course, in order to do that, so we need to transfer the j to take into the other part. Then we have f minus j equal to I squared, that's squared. And we get this multiplication of fj, which is the combination of I squared, j squared, and f squared. So then, doing the same thing that we have here, we will get this. So the relation between the gj multiplied by j, this is what we want to know, will be related to f through the gj. That's the gyromagnetic ratio of j multiplied by the combination of this I minus plus 1 minus f plus 1 minus I plus 1 divided by h squared multiplied by, sorry, without the h squared, multiplied by 2f f plus 1, and this will be the multiplied by the mean value of the vector f. This is what we want to have in this story. And now the only thing that is different here is this factor, the gyromagnetic ratio. And this gyromagnetic ratio is called JF. Right? So at the end, we know that this GJ, the expectation, so the mean value of GJ multiplied by J is equal to GF, expectation value of F. So and this GF we can calculate. So GF is actually depend on I, on F, on I. Sorry, this is not I, this is J. Of course, should be. So here this is I, F, and J, and multiplied by GJ, and this GJ is also connected to L, J, and S. Okay, so everything is connected to everything. But at the end, we have just the gyromagnetic ratio, which will be different due to this treatment. And so the expectation value of the Hamiltonian then in this story, which is now correct in the language which suits the language of this Hamiltonian, because the language of this Hamiltonian is F quantum numbers. So this expectation value now is just a projection, right? So we have to project it on the elements of FMF, right? HB, FMF. So, but this is only the, so here we have essentially vector F, right, in this story. So this gives us, as we know, only the MF as a factor, as a multiplication factor. So we get here the mu B magneton Bohr multiplied by G gyromagnetic ratio F, which is this expression, multiplied by B magnetic field, divided by nothing, and multiply by MF. That's the whole story. Okay, so now this is the end. So this gives us essentially how the energy levels of the atom behave as a function of the magnetic field once you are sitting in the regime, remember, of the weak field interaction. So when the magnetic field is weak, then we have a linear dependence of the energy level, right, on the magnetic field. So it's a linear, perturbation theory. So you get a linear effect. So and this now energy levels actually depending on MF. So now let's take, for example, energy levels of hydrogen atom. So if you remember, hydrogen atom has the hyperfine structure on the ground state. So on the ground state we have F equal to 1 and F equal to 2. So that's the hydrogen atom, right? Hydrogen. This is the distance between them is the distance that you know now very well by heart. 21 centimeters, right? So this distance now is the distance that responsible for hyperfine splitting. So, and this is corresponding to, actually in energy, it's more interesting for us. It corresponds to about, what was it, 10 gigahertz, right? Something like that. The distance between these two in frequency. So this means that I have to consider the magnetic field. So this picture will be correct if my energy of this Hamiltonian is smaller than the distance between these two levels, right? That's the meaning of this weak field regime. So this means that the magnetic field has to be small enough in order to show a splitting of the energy levels smaller than the distance between these two. So let's consider the F equal to 1 state. So F equal to 1 state is the ground state, the absolute ground state of the Hamiltonian, of the hydrogen atom. So, but this level is actually 3 times the generate, right? Because F equal to 1 means that I have the projection on the quantization axis, which is equal to -1, 0, and 1. So MF here can be equal to 0 or ±1. So this means that F equal to 1 state is 3 times the generate. There are 3 levels there. And they are degenerate when the magnetic field is equal to 0. Now you see what magnetic field does. Magnetic field removes this degeneracy because now it's dependent on the MF. So if MF is equal to 0, then there is nothing happening when the magnetic field is applied. So this is equal to 0. So this expectation value is equal to 0. If we actually apply the magnetic field to MF equal to 1, then the energy goes up, right? So this Hamiltonian gives us positive energy, and -1 gives us negative energy. So this means that actually it splits as a function of the energy, as a function of the magnetic field energy. That's 0, right? This is 0. So now we can see that this level goes down, this level goes nowhere, and this level goes up exactly the same amount. So we have here mf equal to -1, mf equal to 0, mf equal to +1. So you know this effect, that's the Zeeman effect, linear Zeeman effect. By some historical reason, it's called anomalous Zeeman effect, as I said you. So it's not very strange, because essentially nobody knew that so many angular momenta are involved in the story. So this linear splitting on so many, people saw so many levels that they actually did not understand why there are so many levels in the story. This is why it's called anomalous Zeeman effect. Anyway, it's the energy here, of course, just proportional to the magnetic field, but the split, so this is correct again, only if this splitting in the energy levels is smaller and this as compared to this distance, right? So the magnetic field should be relatively weak. So, but you know that this is, it's not that difficult to get this magnetic field, well, because you remember what magneton Bohr is, right? So you remember that. I'm sure it's 1.4 megahertz divided by Gauss. That should be divided by h bar. Otherwise, we are in problems. Yeah, well, not h bar even, but h, the Planck constant, not the reduced Planck constant. So this is the frequency per Gauss. So if we are trying to say that this distance is equal to 10 gigahertz, say. So what is the magnetic field that I have to apply in order to destroy, so in order to get the splitting here of the order of this distance? This is, you can see it immediately from this formula. It goes like 1.4 megahertz per Gauss. So to get it to gigahertz, I have to apply 1,000 Gauss. So it's not that huge. It's not a huge magnetic field. Okay, so it's easily accessible in the experiments. So this means that, let's say, up to 1,000 Gauss, it will be still weak field for the case of hyperfine splitting of the ground state of the hydrogen atom, if this is indeed 10 gigahertz, right? So now we are going to consider stronger field. So we want to go to a field which is larger than that. So we can do that, right? So those of you who works in solid state physics laboratories know that this is not very crazy to go to Tesla of magnetic field, which is 10,000 Gauss and even more. So then it's not stupid to ask the question, what's going on if we are going to the intermediate regime? So intermediate regime, quantum number f is not correct anymore, so we have to consider it differently. Let's do that now. So let's go to intermediate field regime. So we're still in the same Hamiltonian, right? But now we have to consider two different terms, right? So instead of looking at this Hamiltonian and saying that now this Hamiltonian is 1, so we know what the energy levels of this Hamiltonian, and this is the weak perturbation, so we have to consider this Hamiltonian as the Hamiltonian with the energy levels. And then we have to consider this part and this part, both of them. So we have to look for the expectation values of these two parts. So these expectation values, again, it can be calculated by closing this by closing this Hamiltonian with energy with wave functions of known energy levels, and then we just have to look for the expectation values of this this Hamiltonian. But remember that two parts of this Hamiltonian is not the same basis. Okay, so then that makes the story a bit more complicated, because the HB, this one, right? The HB part, if we forget this part for the moment, the magnetic field B is diagonal if we consider the basis of J, I, MJ, MI. This is this is where this Hamiltonian is diagonal. So I'm considering J because this two parts of the Hamiltonian gives me J, right? So here the L and S, I can still keep them together. J is a good quantum number. F is not a good quantum number, but J is a good quantum number. So now but hyperfine part of the Hamiltonian, the good basis for that is the basis of is FMF, right? This is we know. So these two guys are living in a different basis space, right? So we need to connect them. So it can be done by different approaches, right? One of the approach that can be taken, so probably more sort of familiar, is to go, you know, to make a transfer from one basis to another basis through Clebsch-Gordon coefficient. So this is not what I'm going to do. So you can still do that. So by the way, what I'm doing here is just sort of a preparation to what you will do at home. So be prepared. I'm not finishing this story, so you will finish that at home. I'm only sort of giving general lines. And then you can do that by two different ways. So one is just going from one basis to another basis by Clebsch-Gordon coefficients, so just to transfer direct. Another way that I'm going to do is just to introduce the ladder operators. So it's also a known trick in quantum mechanics. And using these ladder operators, we will do essentially the same calculation. So we have to do the following. So we have to calculate two parts. One is MJ, MI, A hyperfine multiplied by I, J, and this should be closed MJ prime, MI prime. This is the part of hyperfine interaction plus the Zeeman operation. Zeeman operation is MJ, or the magnetic field operation, MI. This is the vector which walks on GJ multiplied by mu B multiplied by B0, B by B magnetic field, multiplied by JZ divided by H bar. And this should be closed with MJ, MI as well. So one works well, the second one is not very good. So this one we can directly see the eigenvalues here because this is JZ, so J it works on MJ, so it gives just MJ, H bar MJ, so that's straightforward. This is not straightforward because I have to have these basis vectors in order to make this, to calculate these expectation values. So instead of doing that, we can introduce some different operators. So different operators is the ladder operators. I multiplied by j, we can write it as ix multiplied by jx plus iy multiplied by jy plus iz multiplied by jz. That's the sum. And now we can introduce the new operators, j plus minus, and I plus minus, j plus minus will be equal to jx equal to j plus j minus divided by 2. Jy will be equal to j plus minus j minus divided by 2i. These are two ladder operators. Then we can actually say that I multiplied by j will be equal to half of I plus j minus plus I minus j plus I z j z. So it's a different manner to write down the same operator of multiplication of I and j. And this way, essentially, we can take this operator on the basis of mj and I. Because we know what, so you can find the expectation values of this j plus and j minus. So I'm just writing these expectation values. So j mj of the operator j plus minus j prime mj prime is equal to square root of j minus plus mj, j plus minus mj plus 1, square root of that, multiplied by delta function of j prime, delta function of mj prime, plus minus 1, right? So this is why it's ladder operator. So it's just they change the mj state by 1. And the same manner we can write the I plus minus, of course. So if it's I mi between the state I prime and mi prime. So this is the I minus plus mi multiplied by I plus minus mi plus 1, square root of all that, and delta function of I prime, delta function of mi plus minus 1. Okay, so if we know this expectation values, then we can essentially calculate the expectation values of that, of all this guy. And now you, from now on, you are going to work, and so you will be asked to do that in homework. Actually, to get this part of the Hamiltonian, right, to write the matrix, to diagonalize this matrix. So this is not the perturbation theory. So it's exactly the diagonalization. So you will have off-diagonal elements. This gives you off-diagonal elements. Of course, in this story, this is diagonal elements. These are off-diagonal elements. So you will have to find. So you will have to make diagonalization in order to find new eigen values as a function of the magnetic field, so that you will be able essentially to see what's going on with these energy levels once you go to the magnetic field, which is large enough to hit the distance, which is of the order or larger than the distance between the hyperfine states. So you will see how the energy levels behaves. So that's what you will do yourself. Okay? Again, that's one possibility. So if you are not familiar with this, so it's not a small matrix that it's not 2x2 matrix that I'm asking you to do. It's a bit larger. So now it's a real system. So you take the real atom, you take the real number of states that the real atom has. So it's a bit larger matrix, but technically it's not complex to do. And you can do it either by these ladder operators or by Clebsch-Gordan coefficients if you transfer your system from one basis to another basis. Do whatever you want. So I'm not saying you go this way, so go whatever way you want. But please come to the answer. This is interesting. You will see how the energy behaves. So you can expect something to see from the system. So if you start to get some feeling of what's going on, you can expect something. Because this level, right? So now you mix the different energy levels from one hyperfine state and the second hyperfine state, essentially. So this means that instead of F quantum number, right? Quantum number F was the sum of the L, S, and I. So now we had to switch to quantum number J, which is the quantum number J is a good quantum number, which is L plus S. So if we consider these levels, right, so we know what happens with these two levels in a weak magnetic field. So in weak magnetic field, F equal to 1 split it as this structure. That's what we saw. F equal to 1. This is weak magnetic field, energy, and magnetic field. Right, so here you have F equal to 2. Now this level has to be split into 5 sublevels, right? Because F equal to 2 gives you 5 degenerate sublevels. MF equal to 0 will be still linear, right? These two levels will go down, and these two levels will go down, up, sorry. So we'll have 5 levels, right? The splitting, this is the linear part of the story. So exactly the same as we saw here. But now you see that quickly, right, certain magnetic field, right? So especially as I draw here, so the splitting here is very small. So at a certain point, these levels start to meet each other. So they will sort of have to understand what's going on. So this region, sort of a gray region, we don't understand what's going on, suppose. But then what's going on in the higher, at the high, you know, at the higher magnetic field as compared to the hyperfine splitting. So at the higher magnetic field, we know that at J is a good quantum number. So what's J is, right, for the hydrogen atom? J is equal to L plus S, right? So it's L plus S. But L is equal to 0 because this is the ground state, right? So we have ground state, so L is equal to 0. We consider ground state. So that's the hyperfine splitting of the ground state. So L is equal to 0, so we have only S. S is 1/2. So J is equal to 1/2. So essentially what we expect to have is the linear, right, so sort of linear behavior of this type, where instead of MF we will have MJ, DJ. So this means that here at the high magnetic field, I'm sorry, it's not, I don't have, so I have to write here. So it goes down, right? So this goes down. So this level, I will have to find one level going up, right? And the second level going down. So plus 1/2 and minus 1/2. J is 1/2, right? MJ can be equal to 1/2. It goes up. And MJ equal to minus 1/2 goes down. Now, there are only two levels. So, but this is going to be now interesting situation, because now if this part is much larger than this part, but still much smaller than this part, so then I can exchange between these two parts, right, and say that this is Hamiltonian. This one gives me the energy levels, and this is a small perturbation. So then these are the energy levels that I get. This one and that one. And upon these energy levels, I have to add the small perturbation of Zeeman of hyperfine splitting, and I will have here 4 different states, possible states of spin of a nucleus, right? So this is in case that I have f equal to 1 and f equal to 2. This gives me the situation when the I is equal to 3/2. So I is equal to 3/2 is not the hydrogen, right? But whatever. So it's one of the isotopes of the hydrogen. So the hydrogen should be f equal to 0 and f equal to 1. So anyway, but that's not that important. So you will see 4 levels going up and 4 levels going down. So then you start from this strange combination, then you end up with a bunch of levels goes up and a bunch of levels go down. So in between, this is the question: what is going on? So we will see what's going on. So it's interesting. It's a nice picture. Okay. Anyway, let's have a break, 15 minutes, right? And then we will continue to other limits. First of all, yeah, small correction to our discussion. So yeah, the splitting of 21 centimeter is not 10, is 1.4 gigahertz, right? So, and then that means that 1000 Gauss is already quite a strong field. So there everything will be already mixed. So that's just small correction. And of course, what we said, this is not the hydrogen atom. So this corresponds to some spin of the nucleus, which is equal to 3/2. So it can be, for example, rubidium or one of the isotopes or another isotope of hydrogen. Anyway, but everything is correct here. So there is not that much to say about the regime of strong field limit. It's more or less the same treatment, so you have to be more accurate because now you have to split right this part of the Hamiltonian from the story, so and walk with the angular momentum as a good quantum number. L is a good quantum number, but not J. So, and the treatment is more or less similar, so it's not very much exciting to sit there. So it's more sort of technical stuff. So if you wish, you can find how to deal with. I would like to describe this regime, extreme limit, where we need this term. So this term starts to play the role. So we can discuss a little bit about this story. So just to get, so we are not going to treat that exactly. So we just want to get a feeling about what is the magnetic field, what should be the magnetic field in order to get to this regime, right? And what is this, where we can get this magnetic field, a so strong magnetic field, what is the environment that we need? So I can remove that story from here. So it's something that you will play with still at home. Now it's the interesting story is the extreme limit. So we are taking the extreme limit to talk about. Extreme limit. So the extreme limit means that we are essentially need to calculate the a vector potential in order to say something about energy, expectation values of the energy. So for that, we have to introduce the magnetic field, of course. So the magnetic field that we are working is, again, the uniform magnetic field along z-axis, so certain B0z in this z direction. And now this means that the vector potential of this uniform magnetic field is can be obtained from the magnetic field by crossing it with the r vector, and there is a factor of 1/2 in front of that. So this is the vector potential of the uniform magnetic field. So now, if this is the vector potential, we can write down what is the square of this vector potential in order to understand what this term gives. So then we are getting the a square as B0 squared divided by 4, that's the coefficient, multiplied by x squared plus y squared, right? That's how this square value of vector potential looks like. And this is actually the r square, right? So we can just write it as B0 squared divided by 4 multiplied by r squared multiplied by cosine squared theta. So we are now can estimate, right? Sorry, it's not cosine, it's sine squared. Now, what we can now do, we can take the sort of expectation value, right, of this part of the Hamiltonian, and then you see that the expectation value of this part of the Hamiltonian is just the expectation value of the operator r square. Okay, so this is something that we actually know what is the answer of that. So if I want to have the expectation value of the magnetic field Hamiltonian, so it will go like the expectation value of r squared. So it's essentially multiplying, taking into account this prefactor of e squared divided by 2m. I'll get e squared divided by 8 times m due to the 4 that is here, b squared, b0 squared multiplied by r squared, expectation value of the operator r squared multiplied by sine squared theta. So that's essentially the value, and this value we know, we wrote that a couple of weeks ago when we calculated the expectation value of the operator r squared, and so on and so forth. So this gives us essentially the following expression. It's e squared multiplied by Bohr radius squared n to the 4th power multiplied by b squared divided by 8 times m z squared. Z here is the number, is the atomic number. So now this is the nonlinear term, right? The linear term, that's the nonlinear term that gives some contribution to the Hamiltonian. So linear term that gives contribution to the Hamiltonian is proportional to magnitude on Bohr multiplied by magnetic field, right? So that's the linear term that contribute to the Hamiltonian. So it's always some magnitude on Bohr multiplied by the magnetic field. So the magnitude on Bohr we can just write as its value. So it's E charge of the electron multiplied by h bar divided by 2m multiplied by b. That's the magnetic field. So now we can just ask ourselves, so we can divide the nonlinear part by the linear part, contribution of to the Hamiltonian, and then ask ourselves, so that's I would call as a nonlinear part, and this is the contribution into the Hamiltonian HB as a linear part, goes like that. So now the question is, what is the ratio between these two values, right? So once this will be equal to that, then we can say that we are sort of in the regime of a strong extreme limit. That will be, so we can find the value of the B where the extreme limit is relevant. So the ratio between this nonlinear term to linear term, nonlinear to linear term is goes like the E, the charge of the electron multiplied by Bohr radius squared multiplied by n to the 4th power, principal quantum number to the 4th power, divided by 4 h bar z squared multiplied by B. So remember that there exists something like atomic units in the world. So we can say essentially what is important here. Well, you know, even without, no, it's without atomic units. So we just can calculate everything here, or leaving only n to the 4th power and z squared apart. So we can say that this is essentially gives us the n to the 4th power divided by z squared multiplied by the magnetic field multiplied by a factor that gives us charge of the electron Bohr radius squared divided by 4 times h bar. This gives us 10 to the minus 6. Now B should be in Tesla. B should be in units of Tesla to calculate, to give a meaningful value out of this story. So I see here this large suppression factor of 10 to the minus 6. So this large suppression factor means that indeed, until the point where the nonlinear term will be of the order of linear term, we have to go into two different situations, right? So the situation number 1 means that the n, the principal quantum number, should be large. So this can give us a significant contribution for nonlinear term. So if we are working, this is where the Rydberg atom becomes important. So Rydberg atom, again, I remind you, this is just essentially the atom, but the electron occupies a highly excited orbital with principal quantum number of the order of tens and hundreds. So in this situation, if you have, this goes as a 4th power, so it's very strong, right? So even if we have here a few tens, so 100, right? So 100 already compensate completely this factor, and it's more than 1. And this means that if I'm going to very large principal numbers, quantum numbers, or to Rydberg states, this nonlinear term in the magnetic field interactions will be important. Okay, so that's the first situation. The first situation is even for weak magnetic field, even for weak magnetic field, even for weak magnetic field, if n goes to a few tens, then this term, nonlinear term, becomes relevant, and we have to calculate that. But the second limit where this term becomes important, it's when the magnetic field is very large. So, but in order to get the magnetic field which is large, right? So the magnetic field here should be of the order of 10 to the 6, right? So between something which is running between, well, it should be 10 to the 4 Tesla, right? That's unimaginable magnetic field. So I'm not sure that it's something that you cannot really get for free, even not for free, even for every money. So this is the largest magnetic field any money cannot buy. So whatever money you have, you would not be able to get this magnetic field, except if you go to extreme situation. What extreme situation is? Extreme situation is what is the name of this star? Now, yes. Oh, wow. Now there's a name, neutron star. Yeah, right. So neutron star. So neutron stars. People believe that magnetic field in neutron stars is extremely large. At neutron stars, the magnetic field is sort of estimated. Magnetic field is between 10 to the 4, 10 to the 8 Tesla. This is a good number, right? So this number means that if we are putting our atoms inside the environment of neutron star, this means that even the ground state of this atom will be distorted into the direction of losing spherical symmetry. So the spherical symmetry will not be anymore a good symmetry for an atom. So it will be distorted. It will be sort of, you'll get some asymmetry, and therefore the angular momentum will not be a good quantum number anymore. So we will have to do some hard work in order to understand how the energy goes, like energy levels goes, and these energy levels will depend on the direction. So in the direction of the magnetic field, it will be different as compared to the other directions of the space. So these are extreme situations. So this is extreme value, and this extreme value again only relevant when you go to either a very large magnetic field, unimaginable for the environment of the Earth, or you can do that if you are talking about highly excited Rydberg atoms. Then you will have to calculate that more accurately than what we do. In other situations, it's enough to know about weak, intermediate, and strong field limits. So that all these limits will be relevant for different atoms depending on what levels you are working or what magnetic field you are working, or both, right? So that's the end of the story. So that's the end of the story from my point of view about the magnetic field. So now let's have an atom in the environment of the electric field instead of the magnetic field. And let's try to see what is the difference. Now the electric field that we are talking about now is the DC electric field. So just non-varying in time magnetic field, because at the end of this course we will talk about time-dependent electromagnetic fields. This is a different story. Now we are only talking about electric field. So magnetic field is gone. Enough for that. So we played enough with that and play enough with atoms in the magnetic field. Let's try to do some experiments with atom in the electric field. So talking about the electric field is a different story. The differences for the electric field is in the very basic of the interaction of the electric field with the atom as compared to interaction of the magnetic field with the atom. Magnetic field interacts with angular momenta, whatever the angular momenta is, right? So it interacts with, I already removed that from the story, but it interacts with the magnetic moment. And magnetic moment derived from angular momentum, spin of the electron, spin of the nucleus. That's it. But electric field do not interact with spins. It's something to do, therefore the magnetic, by the way, right, the magnetic field, to treat the magnetic field, everything that we had to do is to treat the spin part of the wave function. The radial, or the spatial part of the wave function, angular part of the wave function, that's also a part of the story of the magnetic field, but not the radial part of the function. So electrical field has to do with the wave function, the radial part of the wave function. That's what it's going to change. So how atoms interact with the electric field? So atom is a neutral particle, right? Because it's a combined from the from an electron and from a nucleus. One is positively charged and the second is negatively charged. So with the electric field, it seems to be that it cannot interact. Well, it's interacts very nicely, but of course it should interact not through the first order interaction, but it interacts through the second order interaction. So it should induce the dipole first. So any electric field that you apply on an atom first have to make a dipole from this atom. And then this dipole will interact with the electric field. So you have to induce the dipole. That's the first what electric field does. And then this dipole interacts with the atom. So, and we will see just a few examples. So the electric field, right? So we can get some uniform electric field that goes in some direction of Z. So it's a uniform field. So I put the atom inside. So and what I get in this field is that the atom, the electron cloud is actually the center of the electron cloud is removed as compared to the center of the atom. In the center of the atom, we can consider for the infinitely heavy nucleus, we can consider this center to be at the nucleus. So they actually removed without the electric field, right? We are getting them. So it's probably not very clearly represented here, but the idea is that here this is the nucleus, and the electric field is makes the electric cloud, the electron cloud, to be removed as compared to the center, the central symmetry of the cloud. Of the nucleus. So, and that's produce the center of the electron cloud not at the same position where the center, where the nucleus is. So that's exactly what makes the dipole, right, of the story. So the interaction will be the electric dipole, right? So the electric dipole will be equal to minus charge of the electron multiplied by R. That's the electric dipole. And then the Hamiltonian of interaction of the electric dipole is minus M electric dipole multiplied by electric field. So that's essentially the interaction term. Okay, now what we do, we want to calculate essentially how the states of hydrogen atom will be affected by this electric field. So we need to calculate, again, by the perturbation theory. So we can just take this Hamiltonian to calculate the energy, how this energy of the hydrogen atom will be affected by the electric field. Okay, so now one has to take into account, of course, okay, once we try to deal with magnetic field, we were extremely accurate. We said, okay, there is hyperfine splitting, fine structure splitting, all sorts of corrections and splittings on the energy levels. Now I forget about everything, so we removed everything out. So the only thing that left in the story is this H equal H0. So the Hamiltonian, which includes inside only Coulomb interaction. So we forget about hyperfine structure, we forget about fine structure. It becomes complicated to deal with that. So it's really not simple. Let's just keep the story simple. So what I want to say is just the story of the electric field is not simple. We are not going to do a lot about that. So we will do simple situations, and simple situation, first of all, is to consider the H0 only H0. So the Hamiltonian of the atom is only H0 without any other corrections. So therefore, the energy levels now depend on principal quantum number, L, the angular momentum, and the ML, the projection of angular momentum on the quantization axis. That's it. Okay. Now, this is why there is nothing else is in the story. So it's really just to emphasize that what we need to do to deal with here is indeed the radial wave function and not the spin part of the wave function. Okay, so now we need to close this Hamiltonian HEL between the energy levels of a hydrogen atom in order to calculate this correction. So this is essentially an integral. So it's electron charge multiplied by E0. So this is the E0. It's amplitude of electric field multiplied by the integral over the space Z3R of the psi NLM of R multiplied by Z. Okay, Z, this is a real Z, direction in space. It's not a number, this is not atom number. So this is coordinate. Now it has to be closed. Of course, that has to be also complex conjugate. And this is psi r, z, that's the operator, right? And that's the integral that we have to take. So you can immediately realize that symmetries here play a significant role. So you can understand immediately that this is odd or even, right? That's always a problem in English for me. So what's odd and what's even? Who knows? So what you would call in English izugi? Odd. Okay, good. So that's odd, right? So the operator is odd, and now the question is, if this operator is odd, so the question is, what is the symmetry of the wave function, right? So what is the polarity? I'm sort of forget every single word that I even remembered once. My God, parity, yeah, of course, so many. Sorry for that. Anyway, so this has parity in this, so this wave function has parity, and this operator is an odd operator. So, and then we have to check what is the parity of this wave function in order to understand if this integral will give something. So, if this wave function is even, so it's symmetric, right? So even wave function. So then this integral will be immediately zero. Right? So this and what we know is that wave function of the ground state of the hydrogen, it's a symmetric function, right? So then we can immediately say that for the ground state of hydrogen atom, this correction is equal to 0. So first order correction is equal to 0 for hydrogen atom due to symmetry considerations. Okay, that was easy, right? At least once we consider the situation of n equal to 1, L equal to 0, and of course n equal to 0, this is the ground state of any atom, but it gives you symmetric situation. So then in this situation, so the first order correction NLM will be equal to 0. So in order to see what is the correction, so you have to go to the second order. Okay, in order to see what this correction. So, but before we do the second order correction, let's try to see first of all what is the linear correction. What would be the first order correction? The first order correction will be okay for the first excited state, where this wave function is odd as well. So then everything is okay. So this is correct for if you take the first excited state, for example, n equal to 2. So right for now, this is we are looking still for the linear effect. And this effect is called linear DC Stark effect. So it's linear DC Stark effect, known in the literature, right? So this is the first order Stark effect. It's only non-zero for excited state. Let's say we are dealing with n equal to 2 state. The problem with n equal to 2 state is that it's 4 times degenerate. Right? So it's L equal to 0 and L equal to 1, and L equal to 1 has 3 degenerate states. So we have 4 times degenerate state here. So if it's 4 times degenerate, we have to know. So this is, we have to apply the degenerate perturbation theory. It's not a regular one. Here we have to apply the degenerate perturbation theory. So applying the degenerate perturbation theory, I essentially have to close the operator, this operator, between all wave functions that represent each one of these degenerate levels, and build the matrix, right? And then I have to diagonalize this matrix and see what the new energy levels that I get from this story. So that's the prescription of degenerate perturbation theory. So what we do here, so in this situation, as we said, there are 4 different energy levels. But we actually can say something that you probably don't know, but I know, and I will tell you about that in a few weeks from now. So it calls the selection rules. So this selection rules kills some of matrix elements immediately. So I'm not going to explain right now. So, but I tell you that if you take the matrix element between n, L, m, and of the operator z, and you have n prime, L prime, m prime. So that's the matrix elements that you are looking for. So the only matrix is non-zero only if m is equal to m prime, okay, and L is equal to L prime plus minus 1. Otherwise, it's 0. So right for now, you have to believe me. This is something which is called selection rules. We will talk about that. I promise we will talk about that in a month or so. Once we will start to learn AC electromagnetic fields, so we will come back to that. Now, just believe me. Because if it's not the story, then we are in trouble. So we have the matrix is quite large. But if we are getting only this situation, so this means that I can change the L only by 1. Then I have, and then everything is 0 only if m is equal to m prime. So I have only matrix, in this situation I have only matrix between 2 by 2, because only 2 possibility I have to tell. The only state that is coupled is 2, 0, 0. This state is coupled to the state of 2, 1, 0. And no other situation is possible, okay, whatever I'm trying to do. So because of this selection rules, everything else is 0 due to this requirement. So therefore, the only 2 energy levels out of 4 degenerate levels, right? So probably note them, right? So we have here 2, 0, 0 energy level, and here 2, 1, minus 1, 2, 1, 0, and 2, 1, plus 1. So we have 4 different energy levels here. Only these 2 energy levels can be coupled, can be mixed by this electric field. Other combinations, impossible. Okay, so no this, no that, no this, nothing. Therefore, we have only 2 by 2 matrix to diagonalize, which is simple situation. So we have a matrix with on diagonal elements, 2, 0, 0, which closes the Hamiltonian 2, 0, 0. And then I have on diagonal 2, 1, 0, H electric dipole, Hamiltonian, 2, 1, 0. So this is on diagonal terms, and off diagonal terms is the mixing terms that will 2, 1, 0, H electric closed with the 2, 0, 0. And here I have the opposite, 2, 0, 0 closes this Hamiltonian with 2, 1, 0. Okay, that's the matrix I have to diagonalize in order to find new energy levels. So that's the old energy levels. This is how it would look like. So now I want to find what's going on. So now what we know, that these levels will stay the same, right? So that this level will not do anything, but these levels are coupled together, and they can be mixed, and they will probably be shifted, okay, due to the interaction. So what we can say here is that this is also 0 due to the same requirement. So the selection rules keeps me 0 on diagonal elements. So the only non-zero elements in this matrix are off-diagonal elements, okay? And this off-diagonal elements it can be calculated. So it's 2, 1, 0 that I closes on the interaction Hamiltonian. This is the charge of the electron multiplied by the magnitude of the electric field multiplied by the wave function, right? So the wave function of 2, 1, 0 and 2, 0, 0, these are wave functions that we wrote, hydrogenic wave functions. You have them noted in your notes. So I can just write it. So z to the third power, pay attention, this z means atomic number and not the coordinate. So be aware of strange things happening here, right? So just that's to check your if you're still awake or not. So now it's 16 pi a0 to the third power. Now this is the integral over the space between 0 and infinity. So dr multiplied by r cube zr divided by Bohr radius. So, and it's also multiplied by 1 minus zr divided by 2a Bohr radius. So this is the part of the ground. So this is the part of the 2, 0, 0 wave function. This part is 2, 1, 0 wave function. So this is also has to be multiplied by exponent, of course, that minus z. Again, all z's here are atomic number and not the coordinate. Because here we actually substituted the z, which is the coordinate, by r, because here this is the radial, this is the r that we are interested in, the coordinate. So it should be substituted as r multiplied by cosine theta. This is the projection of r on z. And now here inside the integral we have only r, no z. So everything that is connected to z here is the atomic number. So now it's zr divided by Bohr radius. That's the radial part. And this radial part should be multiplied by an angular part of the wave function, right? So this is from 0 to pi, d theta, sine theta, cosine theta, cosine square theta. That's the integral over theta. And there is another, of course, integral over phi. So that's the whole story, the whole integration. And now this integral can be calculated. It's not very complex, so you can find more complex integrals. And the answer of this integral will be quite simple, actually. So I'm going to write this answer here. So it's a minus E0, it's the amplitude of the electric field, multiplied by 3 times Bohr radius divided by z, large z. That's essentially the answer. So this is how this integral looks like. So we can call this story as, so we can say that, let's say D is equal to 3 times Bohr radius divided by z multiplied by E, right? So minus, that would be the dipole moment. We can call this guy as a dipole moment. So this dipole moment is the charge of the electron multiplied by the characteristic size of the atom. So characteristic size of the atom is the Bohr radius. So everything is okay here. So it's very nice. So it's just the charge of the electron multiplied on the state of effective size of the wave function. So it's 3 times the Bohr. It's an excited state. It's not the ground state. It's excited state. It's a bit larger. So you have here a factor of 3, and you have here the atomic number. So everything is okay. So that's the dipole moment, which is multiplying by amplitude of the electric field, gives you some induced dipole, right, in this story. So essentially, we can say that our matrix that we are writing here I can go up essentially. So the matrix becomes very simple, as we can say that the Hamiltonian of this interaction will be equal to this matrix, which is 0 on diagonal, d of diagonal. I have d of diagonal multiplied by the amplitude of the electric field. That's the only story that is left after all this sort of complex start, or maybe complex start. So, but now, if this is the matrix that we need to diagonalize, so that's analytical, right? Relatively simple, and we can say that essentially the energy levels, so eigenenergy levels, will be equal to plus epsilon 0 d, and the E2 will be equal to minus epsilon 0 d. Right? So one is positive, one is negative, so shifted up, shifted down. And we can also say that the distance between them, of course, is twice the epsilon, 2 times the shift of each of energy levels. So it's interesting to see, right? So we started from this combination of these states. So on this, this was the sort of 4 times degenerate state, 1, 2, 3, 4. So in this state is actually splitted now, right, in the electric field. So 2 energy levels stay degenerate as we expected. So those that are not coupled. One is shifted up, one is shifted down, and this one that is shifted up is actually the linear combination. The eigenfunction of this story is the linear combination of these two, minus psi 2, 1, 0. And the one that goes down is the linear combination of that, of these two wave functions. So the wave function of this level, so the energy level, we know it goes like a minus epsilon 0 d. Here it's a plus epsilon 0 d. So the energy splits. And the wave function is also, there is a certain mixing of this wave function, which is not surprising, right? So we mix between these two energy levels. So this is the mixing amplitude. That gives us a mixing wave function at the end. And it's due to the symmetry of this story, so it's also equally mixed. One is plus and minus minus. So that's the solution essentially of what we can say about how linear DC Stark shift works, or how this electric field essentially change the energy levels of excited state, the first excited state of. So of course, if you go to higher excited states, so you can mix some different energy levels, you will have more mixing. So, but of course, this is something that I removed already from here. There were selection rules that helps a lot to keep the story relatively simple, but you will see some more mixing because more possibilities are existing in excited state. That's how it looks like in the situation. So these wave functions, of course, is not the eigenstates of angular momentum, which is not surprising because we actually remove the symmetry. The angular symmetry cannot survive the application of linear force, so we can really make some sausage out of a nice ball. Therefore, it's expected that the angular momentum is not preserved, but so it's not a good quantum number. But now it's still the ML, the M quantum number remains still okay. So that remains a good quantum number. Okay, so now we can go to complete the story by. We are going to complete the story today, or we are not going to complete the story today. Let's stop here, and we will complete the story. So we need only to complete this story by calculating the second order perturbation of the ground state of the hydrogen atom. That will complete the story, and then we will be able to go forward. I will next week again replace the tutor, and just because I want to. So there's only 2 weeks, I think, left before I'm actually going for 2 weeks. I want to complete a little bit more material before I left, and so next time we will actually finish this, and we will go to 2 electron atoms.